Hi, my name is Chris Gottbrath. I am a technical program manager at Facebook, and I work with Raghu Krishnamurthy and the model optimization team on quantization, but also with other teams on performance optimization and various different compute backends used within PyTorch. It's my pleasure today to be able to talk to you about what we've been working on in the area of quantization and review both the basic functionality of quantization that we've been adding over the last year or two to PyTorch, and also some of the new things that are available in preview in PyTorch 1.6. The outline for this talk will be pretty simple. We're going to talk first about the motivation. I'll talk about a couple of different forces and factors that are driving our interest in quantization. And then I'll talk about the three basic workflows that you'll probably want to use if you want to quantize a new neural network model in PyTorch: dynamic quantization, static quantization, and quantization-aware training. And then finally, I'll talk about some new features and new capabilities that we've introduced in PyTorch 1.6. These are graph mode quantization, which makes it kind of radically simpler to apply quantization to a neural network model, and then also the Numeric Suite, which gives you a much deeper view into the numeric behavior of different choices in quantization. So in terms of motivation, the first motivation for quantization is simply that machine learning, fundamentally, it's the machine learning is a technique, deep learning is a technique that is very compute intensive, right? Like we know the models, neural network models started getting really accurate and also got very large. And that trend has definitely continued, maybe even accelerated in the recent years, so that some of the most uh, cutting edge accuracy models are also extremely large. If you look at BERT and Megatron and other kinds of things, you'll find that they have just an enormous number of parameters. They're extremely accurate, but they use a significant amount of compute resources if you want to train them and if you want to run them for inference. So this is a trend that seems to be continuing and moving forward. And um, I guess I'll say a couple words here, but it's probably pretty obvious to anyone who's used, let's just say, a speech recognition system like Siri or Ask Google. As those machines have, as those capabilities of those models have improved, the user experience has improved greatly. And of course, I don't know about you, but I feel like there's still a long way to go for those systems to be able to comprehend more and more speech, more and more accents, and more different noisy environments. So there's a lot more that can be done, but the experience is qualitatively different um, as you achieve different plateaus of quantitative accuracy. So obviously, as we're trying to provide better and better services, we're gonna need larger and larger models, and that's something we need to. When we say deal with, when we think about Facebook scale, that can be a huge deal. We have data centers all over the world, and they are quite large because we're serving billions of users. And if we start talking about deploying neural network models, especially really big neural network models, in order to provide features in those data centers, the cost and resource usage can be very immense at Facebook scale. So we're already seeing data center power consumption doubling every year. If we start thinking about applying some of these advanced models, that's going to push that trend up even more, and that's something that I guess it's fair to say we're highly motivated to try and avoid. Facebook isn't just what happens in the data center, though. We're a highly mobile, in a mobile-first environment and set of apps, and of course, we want to put capabilities at your fingertips, um, but that's kind of the mobile devices, cell phones, they have a lot more memory now than they did before, but they're still very small and low power usage compared to data center servers. So there's a lot of interest on our mobile side as well to try and drive efficiency, try and drive model size reduction, and try and make sure that we're being appropriately using things like the battery resources in mobile devices. So there's a lot of interest in techniques that we can use to optimize, get better performance, and reduce the energy usage in mobile. So the technique that I'm going to be talking about today is quantization. And with quantization, the idea is we're going to use a reduced precision to store the individual values within a neural network. And by doing that, we can unlock model size reductions and also often much more efficient and faster kernels. So this is a technique. This technique that I'm going to be talking about, and it has opportunities to provide really significant efficiency improvements. But I don't want to make the story seem like quantization is the only thing you can do to improve the efficiency of neural networks. There's a whole host of different techniques, and at Facebook we're pushing on all of these kind of simultaneously in order to pull that energy consumption curve and cost curve down for our data center and to enable more complex models to be deployed in mobile devices. So the other tools that we're using are optimized kernels. So even within a given precision, even without thinking about quantization, we can optimize the various different numerical operations that we use within PyTorch and reduce data center power usage. We can also use different hardware accelerators. There's cool things like the Google TPU that are out there. There's advances in new generations of GPUs that are available, and so we're trying to apply, and also on the CPU side. So we're trying to apply those new technologies into the data center and into what we're trying to do here at Facebook. There's also our research organization FAIR is pushing the envelope on efficient network architectures. So there are things that are available, and there are big advances that have been made, especially on the convolutional neural network side with mobile networks and MobileNet, FBNet, NASNet, etc. That simply require less computing horsepower to deliver similar results for certain workloads. So we're pushing on all of these fronts at once, but quantization is a really important tool in the toolkit. So to provide a little bit more context on how quantization actually works, if you think about neural networks, they're fundamentally doing they boil down in a lot of cases to a lot of matrix multiplication, tensor multiplication, tensor addition kinds of operations. So you're taking lots of floating point, typically floating point 32 values, you're multiplying them by other floating point 32 values, and you're adding the result together and accumulating that in order to create a new floating point tensor. The question, or the promise of quantization is, well, what if we approximated that? What if we got an approximate solution by multiplying an int8 value representing the weight tensor and an int8 value representing a value in the activation tensor to get the resulting output tensor, and that int8 value can be basically representative of the floating point value. You could have a linear transform, for example, between them. So you have a quantized int8 value and a 0 point and a scale factor, and you can represent a floating point value. This turns out to work and be actually really powerful. So it allows you to take up less memory on the device, because your tensors now are suddenly being represented with int8 values at every point rather than FP32 values at every point. So it's simply 4 times less memory, plus some scale factors, which are usually very small compared to the size of the tensors. And then with modern hardware on the CPU side, on the GPU side, and also on the DSP side, all three of those hardware families our partners are rapidly adding new instructions and new capabilities and things like that allow us to really efficiently run compute in int8 or in FP16 or bfloat16. So basically on the hardware side, and by looking at the way neural networks run, we've discovered that we can apply these approximations and actually still get relatively robust results. Now you have to be careful in doing it. So there's some networks that are really forgiving, and it's kind of amazing. You can basically just quantize them, do per tensor quantization, and the end result is almost as accurate as the floating point value. And in those cases, that's great. We can apply that really quickly and easily. In some networks, they're slightly more demanding. They're slightly less forgiving of the approximation. And so you'll see as I go through the rest of this talk, there are some techniques that you can use to achieve a pretty high accuracy, even in networks that are a little bit more demanding. So maintaining accuracy can be hard. It can be easy, but for some networks it's hard. And we provide you lots of tools in PyTorch in order to be able to maintain a good accuracy even in the more demanding models. Okay, so that's kind of the high level, like mathematical, what are we doing when we're quantizing. Now, how do we deliver this to you in PyTorch? So there's kind of three, I guess, principles that kind of drive the way we're doing this. One of them is easy to use. So we're really trying to make this be as turnkey as we can. So we've clearly documented the three different workflows that you use, and in each one of them we've tried to reduce the number of steps as much as we can. Now in some cases there's still a number of steps, but we'll talk about that later. This is three key workflows that we'll talk about here in a few minutes, and those are well documented. We also recognize that we don't know everything yet, right? Quantization is still kind of an active area of research, and PyTorch is loved by researchers because it gives you the ability to get in and tinker with things in Python dynamically. So we've similarly implemented quantization in PyTorch by giving you a lot of tools directly accessible to you. Now, the workflows will make it easy to use, so you don't have to dig into the details, but if you want to dig into the details and tinker and find your own way of quantizing things, if you want to apply some really fine-grained controls to things, you totally can do that. And you can push the envelope of quantization research using PyTorch quantization. And then this is important to us, so we have put PyTorch quantization into the core of PyTorch. So the Q-tensor is a fundamental thing in PyTorch, so yeah, shouldn't feel bolted on or an afterthought or a third-party module or something like that. It's a core functionality within PyTorch. And we've, for the key compute backends that we use a lot, like FBGM and QNNPAC, the quantized kernels are just right there next to all the other kernels within PyTorch. Excuse me for the cough. Okay, let me talk you through a little more detail of how this is organized inside of PyTorch. So if you're familiar with PyTorch's internals, you'll be able to kind of map where you'll find things. We want everything is sort of found. I'm going to focus on kind of the right-hand side of this slide here. Everything is founded on the notion of a quantized tensor. So the Q-tensor in PyTorch is basically just like the tensor you know and love, except for that there's a scale factor and a bias sort of stored as part of the tensor. And you can operate on those Q-tensors in the same way you would a normal tensor, and they just have to be stored in such a way that they are quantized, and they can be taken advantage of with quantized ops. Now, how do you get a Q-tensor? Well, we have torch.quantize per, and then there's basically a conversion utility that you use to create a quantized tensor from a non-quantized tensor. And there's two variations of this, which are kind of shown here on the slide. There's a per tensor quantize or a per channel quantize. Let me quickly explain what the difference is. So when you're creating a quantized tensor, you're going to need some scale factors because you're going to map between the int8 value and the FB32 value. It's basically a multiplication by a scale factor. Now we have one scale factor for the whole tensor, and that would be a quantized per tensor, and that will give you a single scale factor for the entire tensor, and all the values will be, if you think of it, starting with the floating point value, you're dividing by the scale factor, and that gives you the quantized value, right? Or we could do a scale factor per channel. So that's the torch quantize per channel operation will create a tensor which is quantized in a per channel fashion. So you now have, instead of a single scale factor, you'll have a scale factor for each one of the channels. So if you have 20 channels, then you've got 20 scale factors. If you've got 150 channels, you've got 150 scale factors. Pretty simple. Okay. Then we need to have operations that can operate on Q-tensors. So those live in the code base as under torch.ops.quantized. So you'll find the 2D comps there and the linear there and things like that. Now you also have higher level operations, the torch.nn module, which has the sort of key modules that you use in a lot of neural networks. And so you'll find the torch.nn quantized and torch.nn quantized.dynamic contains sort of analogs of a lot of the routines that you're used to using in PyTorch to create your models. You'll also need some tools to convert, to work through the different workflows that I'll talk about in a few minutes. You'll see those live in PyTorch in the torch.quantization namespace. So you'll see like a prepare and a convert and things like that. Those will live in torch.quantization. Some examples of those, and actually two that I'll just highlight here, are torch.quantization.observer and torch.quantization.fakeQuantize. Observer is used to choose the scale factors, which we talked about before, in the quantized tensors based on observing the extents of like activation tensors for a calibration data set. And torch.quantize, fake quantize is used in the quantization aware training to simulate the effect of quantization. So these are basically like helper functions that you'll use at different points in the workflow. So this is also, it's worth noting, an extensible API. So we've got this sort of layout here, but you can extend it and add your own quantized ops. You can add your own observers. You can also go in and tinker with exactly how you map based on observed characteristics of the tensors during calibration. How do you actually choose the quantized values? So there's different techniques, numerical techniques that you might want to use. We implement a few of the basic ones, but you can implement your own pretty easily in Python. Okay. Now, based on those building blocks, let me talk you through the three different workflows. And this is kind of the introduction to the main body of this talk. So we're gonna show you in detailed slides how to apply each one of these three different workflows, either dynamic quantization, static post-training quantization, or static quantization aware training. But at this point here, I just want to highlight the pros and cons and when you would use each one. So dynamic quantization, this one is one you'll use for basically IO-bound networks, such as LSTMs and transformers. In this case, what we're going to do is we're going to ahead of time, we're going to quantize the weights so that the network can store all the weight parameter tensors in, say FP16 or int8 format, so in half the space or a quarter of the space as the FP32 network. So it immediately gives you benefits when you're loading in those parameters. At inference time, you're loading in a half or a quarter as much memory bandwidth. The activations, those get quantized dynamically at runtime. And so the pro of that is that you are always getting a good scale factor chosen given the data that you have. It's always sort of fine-tuned for specifically what the input data set is at that given time. The downside is that means it has to dynamically make that decision at runtime. So at runtime, it has to look at usually the range of the input tensor and figure out what scale factor and offset will work best to quantize that range of input data. So there's a little bit more math every time it's transforming the data from for a new Q-tensor on the activation side, but it's kind of like always well-tuned for the data. So this tends to give good accuracy, and it tends to work well when the performance is memory bound due to weights. Static post-training quantization, on the other hand, in this case, we are quantizing both the weights and the activations ahead of time. We're choosing the scale factors for all of those ahead of time. This tends to work really well for CNN type networks, which are heavily compute bound. and where you have kind of large input data sets that you want to be able to really quickly quantize. So that leaves the open question. Well, how do you choose? It's easy to see. Well, it's not easy to see, but it's relatively straightforward to see how you choose how you quantize the weights because they're known ahead of time. The activations are novel. Each time you point a camera at a different thing, you've got a new set of input tensors. So what we do is we do a calibration process. So you'll add a new step to your model development or deployment workflow where you calibrate the data, or so you calibrate the quantization based on some input data. And that's used to determine the scale factors for all of the activation tensors. This tends to work pretty well for a lot of neural networks. There are a few networks in particular, like mobile CNNs, that tend to not give the best accuracy with static post-training quantization. So what we encourage you to do in those cases is to do this quantization-aware training, and this requires a little bit of fine-tuning of the model, so it's a little more complicated and a little more labor-intensive, but it can often recover a great accuracy for these mobile-style, relatively fewer parameters, CNN-type models. Okay, and I'll take, if you didn't follow all of that, it's okay because we're going to walk through the details of each one of these in the next couple of slides. I'll just try to give you the overview here. So let's talk about the first one of these three. Top row of our table a moment ago was dynamic quantization. So this is for your sequence-to-sequence type models, your transformers, your BERTs, your LSTMs, and your multi-layer MLPs, multi-layer perceptrons. Sorry, I stalled pulling up that name. Okay, so here, this is going to do, there's no extra calibration required for this, so this actually is really streamlined. So you start, let's go over the code here on the right-hand side. You're going to start with a language model. You're going to load that model in. You load in the parameters for it for the state diff. So now you have a full model in PyTorch. I'm going to pass that into the quantized dynamic helper function in the quantization module. And that is going to, and you're going to pass in the data type that you want to quantize to. Like in this case, it's a QU int8. And now you have a quantized model. And you know what? You're pretty much done. You can now use this quantized model and it will run fast and give you your quantized accuracy. You can also save this model. You could script it. So you can run it in an environment in a C++ environment, such as what we use in our data center for deployment. So this one actually fits on one slide. It's a super simple process, and you basically just quantize the model, and you get a quantized model. Again, underneath the covers, what's happening there is it's going to look at the weights because it knows them, and it's going to figure out what the right scale factor is for those, and it's going to create quantized tensors for those weight tensors. And then the activations, when you run this for inference, it's going to look at the range of the values in those activation tensors, and it's going to dynamically choose the appropriate scale factor to represent that data with the minimum loss of accuracy, and it will use those. It'll apply those scale factors right away. So it's determining each given time what the right scale factor is. This works again well for LSTMs, transformers, MLPs, things like that. Tends to give you we're seeing things like 2 times faster compute, 1.5, 2, somewhere in there, and then generally 4 times less memory because these tend to have lots of parameters. Okay, second workflow, post-training static quantization. So this is what you use for most CNNs, in particular CNNs that run in the data center. Here, you're going to have a multiple step process. So this will take a couple of slides to describe. At the high level, what we're going to do is we're going to make some minor model modifications. Here we describe that as kind of tweak a model on the left. Then you're going to calibrate the model based on some data, and then we're going to convert the calibrated model to a quantized model, and then you'll be able to run the quantized model and get the high performance. What's happening underneath this covers is that this is quantizing the weights and the activations for the entire model based on what it saw in the model in terms of the parameters, and then what it saw for the calibration process in terms of the activations. This works really well for CNNs, particular data center type CNNs like ResNet, ResNext, etc. This tends to give a faster compute and also uses less memory, both for runtime and in storage. In the calibration process, you're basically putting around the quantized kernels, like COM2D, you're putting these observers in, and they look at the values that are coming in. They look at the range. They basically store the statistics, and then they choose the right scale factor. And then when we quantize, then you'll go through a convert operation to quantize the input values, and then you'll just use int8 values through the entire network. So you're not reconverting back to FP32 between each individual layer. So it's one of the nice benefits of this post-training static quantization. Now, how do we actually apply this? So this is now the first of this would be like, I think, 3-slide sequence, maybe 4. We're going to just show you the pseudocode for the main operations you do when you do this. So the first step is we're going to load in our model over here. We're going to load in the weights, and we are going to put the model in evaluation format. That turns off some of the training characteristics of the model. So it'll replace your batch normalization, for example, with a scale factor. And so that's what the model.eval does. And then the next thing we're going to do is we're going to slightly tweak the model with this fuse modules routine. Again, it's a helper function in the quantization namespace. And in this case, we're telling this, for example, that conv, batch norm, and ReLU, when you see that pattern, we want that to be replaced by a kind of a wrapper module, which will be a conv ReLU 2D. That conv ReLU is what we actually have a nice fast version of conv ReLU for quantization. So we want to be able to apply that. The other thing that you do at this stage is you make sure that you have unique names for various different layers, which could mean some like minor model rewriting. It's kind of routine, but you want to do that. And then the other thing you do here is you may apply you can go in here and choose where you want to convert to and from quantized forms. So you can actually choose to quantize only a subset of the whole neural network, and you can do that by doing some minor tweaks to the model at this stage in the process. Okay, once you've done the sort of minor model modifications that we talked about on the first slide, the second slide we want to set our quantization configurations, which is the qconfig parameter you can see mentioned here. There are a couple of different things that are included in this. One is you can apply some blanket rules to the pattern matching that happens later on to basically identify which modules within the model you want to have quantized. So you can turn on and off sections by using qconfig here. The second thing that you can do is you can choose like the exact form of quantization that you're taking. So you're doing things here like determining whether or not you're going to have a non-zero bias, or whether you have a constraint that indicates you always want to use a bias of 0. Those kinds of things are part of the qconfig set of options. Nice thing is you don't need to kind of know the details in a lot of cases. So if you're on the CPU, PyTorch on the CPU generally by default uses the FBGM fast math library, matrix multiply library. And we have default qconfigs for FBGM. So you pull that in, that will tell it the set of modules that FBGM has nice operations for, and it will set the numeric parameters to the right thing for FBGM. There's a similar set of default parameters for the QNNPAC library, which we use on mobile devices. So yeah, pull those in, and you can override anything that you want to, but you'll at least start with reasonable defaults. And then the important step here is we want to prepare the model for calibration. So you can see the line here that shows the Q model, and then we apply the quantization.prepare function to that, and we get a new Q model which has basically observers placed in around all of the important quantized routines to observe the activation tensors and see what their ranges are. Now that we have the observers in place, we want to put our Q model into evaluation mode to make sure that that's I think it's redundant, but we want to do it again here just to make sure. And then we want to evaluate the model over some sample data. And this doesn't have to be your entire training data set. It can be a subset. Usually a relatively small subset is enough, but you want basically enough data for the statistics to be gathered, reasonable statistics to be gathered for the values of activations in all the different layers. So having done that, it stores the values right in the Q model right there in PyTorch. The print statement here on the right hand side shows what that looks like. So this convrelu2d, which we created in through the fuse module pass, you can see that it's decorated with the min-max observer, and the min-max observer has a min value of 0 and a max value of 4.55. So it's basically recording some statistics about the values that are in the floating point tensors that are being used for activations as an input to this convrelu2d, and we'll use that to set the scale factor in the next step. And you can create your own observers, which might have different statistics. If you don't want to do min-max, you might want to do something which is more statistically based on the centroid rather than the extreme values. So you might do something that takes 80% of the maximum and allows some things to saturate. That's your choice, and you can create those observers and implement them. Okay. Having prepared the model and then run that, which you inserted the observers, and then you run that over the calibration data set. Now we have the statistics we need to be able to actually create the quantized model. So these command here, quantization.convert, where you pass in the Q model that has already been calibrated with the calibration data. The convert command does the rest. So it goes through and it replaces all the operations that can pattern match with the appropriate quantized versions of those operations, and it uses the statistics that were gathered in the observers and are recorded in the model there to set the right scale factors. And you can see when we printed this out here, you can see it says quantized convrelu2d. So it's now using the quantized version of that fused convrelu operation. And you can see that there's a scale factor in there, and that scale factor was informed by the statistics we gained in the previous step. So it has a scale factor of 0.035 and a 0.0. So it knew to do that because you calibrated the network in the previous step. And yeah, the end result of this is the next slide here just shows, in order to use it, you just use it, right? Like you've already got a quantized model, you can call it right away, and it will call into the quantized operations, and it will do all the right thing to convert all the tensors into the right format. You can also use the JIT script mechanism to script this so you can run it for C++ inference. So you can deploy it to a mobile backend, for example. And that's all it takes. Now, it was a few steps. It was 4 slides worth of steps, but they're pretty straightforward. You start with a model, you tweak it a little bit to make it more amenable for quantization. You make sure it's in evaluation mode. You do the prepare step to put it into put in the observer so that it can be calibrated. Then you calibrate it on some data, and then you convert it. And at the end of the convert step, you now have a fully quantized model, which you can immediately run in quantized form, or you can save it to disk. All right, so let's just step back here a little bit. So we've talked our way through the 2 of the 3 workflows. We've talked about dynamic quantization, that all fit in one slide, that you use that one for LSTMs and for transformer and BERT type models. The second set of slides were the post-training static quantization, which is generally, you will find pretty good behavior for CNNs that are used in data centers and things like that. Sometimes you will encounter a CNN that just doesn't give good accuracy when you do post-training static quantization. In those cases, then you want the next technique that you can reach for is called quantization-aware training. The idea of quantization-aware training is that we're going to fine-tune the network in such a way that it learns how to give the correct answer when its inputs and weights have been quantized. So basically, we're going to go through a fine-tuning or training several epochs where we're touching up the weight values such that when they are later quantized, they're going to do a better job of giving the right result. So basically, the network learns a little bit how to work better when it's been quantized. I believe it also will do backpropagation on choosing the scale factor. So instead of just mathematically determining what the scale factor should be, we can actually learn those as well. I'm not 100% sure on that, but I think maybe we do. Maybe we do that as well. But in any case, the result of this is that you will get a model which often has higher accuracy, closer accuracy to the FP32 value, even though it's using quantized inputs. How do we do this? We do this by basically rounding the values in a way that emulates the quantization. So if you think about int8 quantization, you're choosing 256 values. You only have 256 value vocabulary for all of the activations and weight values. So we can emulate that. We can basically have the same behavior if we continue to use floating point, but we round them such that they are rounded to one of 256 discrete and evenly spaced values. And then that will basically give the same numeric characteristics as if it had been quantized. But it's still floating point, so you can still do backpropagation in the normal way. So now let's show you how you actually apply that. It's actually very similar to post-training quantization, except for instead of calibrating, you're instead doing fine-tuning. So first part here should look very similar. You're starting with your ResNet, you're loading in the parameters. Then instead of turning it into evaluation mode, you want to leave it in training mode. So model.train, that says leave yourself in training mode. And then we want to use the fuse modules to again fuse our conv, batch norm, and ReLU. And you can see here it's creating a conv, batch norm, ReLU 2D with all three of those different layers. And then you mix, similar to make sure you have uniquely named layers and things like that. Okay, next slide. Here you're going to prepare your network just like you did before. So again, we get our model qconfig for FBGEM, but we're now using the get default QAT qconfig because we want to have the quantization aware training version of this. And then we want to use the QAT version of the prepare command, which will, instead of putting in observers, it will put in fake quant nodes. So now we're going to be able to then subsequently train the model and have it basically round the values that it's using so that they look like they're quantized. And that's what the next line does here. We train our model using training data, and instead of training normally, it's going to basically use these fake quant nodes to round the values so that it looks like it's been quantized. So you can see this is the printout of the values, and you can see that this has been decorated now with these fake quantized nodes. They're accumulating different parameters as they are doing the rounding. And the rest of the workflow is pretty much the same. So once you have done this, once you do so you prepare, and now you train instead of calibrate. Once you have the trained Q model, you then just do a convert, and then you have a quantized model. So instead of being informed by the observers, you'll be informed by the data that's gathered by the fake quant nodes, which give you the ranges and the scales and things like that. And it'll create a quantized model. But the training process is also changing the weights in the model. So this Q model now not only is quantized, it's also been fine-tuned so that it will run better in a quantized fashion. So that's the third of the three models. So let's look at what the accuracy looks like for each one of these. So let's look at three different types of models in different domains. So ResNet is our frequently referenced data center convolutional neural network. The standard FP32 accuracy for that is 76.1. When we apply post-training quantization to that, using the workflow that I just showed here, you might see an accuracy drop of 0.2. That's pretty common. What do you get for that accuracy drop? You get the runtime performance, the latency dropping from 214 milliseconds to 102 milliseconds, and the memory use dropping by about a factor of 4 modulo some scale factors. So you use a quarter of the memory, and you use half the time, and you lose 0.2 of your top one accuracy. Okay, so that's pretty awesome. I'd say that's in many times that'll be a win. Right now, maybe you're in a really accuracy constrained state and you don't want to drop 0.2 percentages of accuracy, but in many cases that'll be an acceptable trade-off. MobileNet V2. Now this is one where we find that we need quantization aware training. And on my next slide, I'll do an ablation analysis so you can see how much benefit you get if you did it with just post-training quantization. But in any case, with the best technique, quantization aware training applied to MobileNet V2, we typically see 0.4% of accuracy loss on the top one accuracy. And here, looking at what the performance looks like on a mobile device like a Snapdragon 835, we see that we can run inference in 18 milliseconds that would have taken 75 milliseconds. So that's almost 4 times faster. So that's pretty awesome. So you get 4 times faster, you get a quarter as much space, and you only have to give up 0.4 percentages of points of accuracy. BERT, this one, dynamic quantization with per channel quantization actually gives you pretty much identical accuracy results. So 0 drop in accuracy. It's 90.2 before, 90.2 after, and it runs in not quite twice as fast on the server with a batch size of 1. It runs in 313 milliseconds instead of 581 milliseconds. And again, in terms of memory usage, it should be a quarter of the memory usage, modulo some scale factors. So pretty big benefits for relatively small drops in accuracy. The quantized torchvision models are available. We've gone through almost all the torchvision models. We've created quantized versions of them. I think we've even uploaded the quantized reference weights for those, and those are available right in torchvision. So just look for a quantization subdirectory of the models directory, and you'll be able to see all those and use them right away. Okay, so I mentioned that we would show an ablation analysis in the last slide, so here's that relatively quickly. So this is MobileNet V2. I remember I said the winning technique was quantization aware training, and you dropped 0.4 percentage top one accuracy. But if you were to only have applied per tensor quantization, you would have dropped 6% accuracy. Again, I mentioned this before, but I'll just quickly touch on it again. There's 2 ways there's 2 forms that Q-tensors can take. The simplest form is the per tensor quantized, and there we have a single scale factor and offset for the entire tensor. So you have all your different channels, all your different heights and width values, and you basically put all of them in a bucket and you look at what the right scale factor is to express all of them, and then you use that scale factor, you apply it to all of them. That will give you some good results for some cases. Some cases you want to use per channel quantization. In that case, instead of having a single scale factor, you have a single scale factor per channel. So if you have 100 channels, you have 100 different scale factors, and each one is tuned to the data that we observe in that channel, or that we when you quantization aware training, that you train and you sort of see happening in that channel. So that's the difference between per tensor and per channel. You can see that per tensor is dropping 6%, per channel is dropping 5%, so it's better, but still not awesome. Quantization aware training, where the network learns how to give you the right answer even in the presence of quantization, for MobileNet V2 seems to be necessary, and it gives you a much more respectable 0.4% accuracy drop. So you can see kind of the relative importance of each one of the different techniques. Okay, again, kind of the pattern we've seen is that for data center type, like full size CNN models, usually post-training quantization with per channel with or without per channel is enough to give you good accuracy. With some of the reduced parameter mobile type networks where they are kind of, I guess they have fewer ways for the signal to propagate through the network. Maybe. Those seem to be the ones where you need quantization aware training. So that's the sort of pattern we're seeing. I don't know that we can promise. Okay. So with those slides, I've gone through all the current capabilities in PyTorch quantization. You've got so a lot of tools in your toolkit. Let me talk a little bit about some of the stuff that we're building to make things even easier. So you will remember that when we did post-training quantization, it was several steps. You had to prepare your model. I talked about different things. You had to like manually fuse your conv-rel-u in order to get good behavior. We'd like to make that go away. It's a routine thing that you should apply to every single model. We should automate that. So what we were doing is something called graph mode quantization. So here, what you do is you script your model first. So you can see the first row in this instructions here is to take your model, run torch JIT script on it. You get a scripted model. What's happening underneath the covers when you do a scripted model is we actually construct a graph for that model execution. So in this case, PyTorch is generally an eager mode framework, which defines the network by running, and it does not try to construct a network, a graph ahead of time representing that network. For scripting and running these networks efficiently on deployment hardware, we do create a graph. Once we have that graph, though, we can use our graph mode quantization to modify that graph. So the graph mode quantization flow starts by scripting your model, creating that graph. Then you can use prepare_JIT and pass it in a model, and you'll get it'll automatically apply all the things you need to do to preparing the model. You don't have to go through and manually fuse your modules or make sure that you have unique named modules or things like that. You can just use prepare JIT and it'll take care of all the details. And then you can do calibration, same as the normal workflow, and you do convert_JIT, and it will automatically convert it into a quantized model. And it's already been JIT-hid, so you can just save it. You don't need to do separately a JIT process. This is kind of work in progress. We think it's stable enough for people to use. It's a prototype feature, but we're still tweaking around the edges. So if you'd like to use this, then you go to the PyTorch download mechanism where you would normally download the stable release, and instead check nightly, and you'll get a nightly build, the most recent nightly build, and that nightly build will have this capability. Alternately, you can just go and clone the GitHub repository for PyTorch and build it yourself. If you're building off of master, you're going to have this graph mode quantization available. So either build it yourself from GitHub, or go ahead and download the nightlies if you want to take advantage of this. And then the other new feature, which is in prototype, is our Numeric Suite. So we have found in some cases when we're working with kind of tricky networks that you want to go in and maybe turn off quantization for a particular layer, or make a choice between, well, can I use FP16 or int8 for this particular network, for this particular part of the network. For those kinds of analysis, we found that it's really helpful to break down and basically look at the accuracy impact of different choices on a layer-by-layer level. So the Numeric Suite is some tooling that allows you to do that. It will basically compare the intermediate outputs between a FP32 model and basically you run the model in the Numeric Suite, and it kind of automatically runs the model both in floating point and in quantized form, and it allows you to compare the results between the two. I think it actually runs it in both, and it propagates forward the FP32 values, and it requantizes it, passes it into the quantized. So you can see on a layer-by-layer basis exactly how much each layer is being, how much accuracy lost is potentially sort of building up in each layer of the network. So it's a really cool technique. It's available right now in nightlies. It supports static and dynamic post-training quantization. We're working on quantization-aware training. It's not there yet, but that will come in the future. Right. So I've covered now our 2 new features. I've covered the basic 3 workflows. This slide just kind of gives you an idea of how much what coverage we have of the different operators. So I think the key operators you need for CNNs, for transformer style models, for RNN type models, and for multi-layer perceptron type models are covered here. But we definitely don't have every single operator in PyTorch, so there are some gaps. Do let us know if you have a network that falls into one of those gaps, and also feel free to contribute quantized implementations if you'd like. I've mentioned these 2 backends several times previously in the talk, but I'll just kind of reiterate here that we have quantized support in both FPGM for x86 CPUs and also QNimpact for our ARM platform. So for mobile PyTorch is quantized using all the same workflows that we've talked about here for data center PyTorch. Right, and here's my final slide. Thank you. Looks like we're about 15 minutes into the recording, so it took a little bit longer than I thought. But I just want to reiterate that PyTorch has been, we've been working on quantization since PyTorch version 1.3. We're at version 1.6 now. So it's had a little bit of time to stabilize and bake. I think it's very much ready for you to use. We're using it in a lot of workflows within Facebook. We have full documentation available in the regular places on PyTorch. We also have quantized tutorials walking you through all the different workflows that we've talked about here. We've also worked with the torchvision team to make quantized versions of all of those key, frequently used torchvision models available. Basically, that means you don't have to figure out exactly what, when we said the prepare model step, you don't have to take that step if you're using a ResNet or or GoogleNet or one of those. You grab those from torchvision and you can start from there. You can modify it if you using a variant of one of those networks. You can look at the torchvision once for reference to see what the quantization changes were we made. And then I just want to reiterate that we have these 2 new prototype features in 1.6. One of them is the Numeric Suite, which gives you better visibility into how your model is responding to quantization. And then the other one is the graph mode quantization, which is a big step along the path of making this all very extremely turnkey for a wide range of different models. So thank you very much. It's been good talking with you, and I encourage you to try out quantization and definitely give us feedback on the forums or through other channels as you do so. Thank you very much.